Today we're finally going to get to some bottom line analytical types of things, all related to resolution. So the emphasis today is now on two peaks that are not completely decoupled from one another, which is, of course, the simplest situation that you ever run into, because normally you're dealing with a significant number of peaks, and so you actually have to worry about clusters of something coming in on both sides of a particular peak. But two is a good place to start. So I'm going to again review. Let me turn on my pen. We're going to review the definition of resolution, and then we're going to get into the heart of those papers by Snyder. By the way, I sent by email both papers, so you don't have to go hunting for them in the 70 paper collection. There's at least 5 papers by Snyder in there, and it may not be evident which 2 papers I was talking about. So we're going to look at the impact of resolution on 2 overlapping peaks, peaks of the same height and peaks of different heights. And it's really very important to be able to look at a chromatogram and say, oh, this resolution is good enough. Or, oh, I got a problem here, and I have to work on getting these 2 peaks better pulled apart. And we'll be talking about what are the most important factors in getting peaks to pull apart. We'll look at the actual analytical error when you measure the peak height when 2 peaks are overlapping with one another. If 2 peaks are perfectly decoupled, if they're perfectly resolved, which generally means a resolution greater than 2, there's no error. But as 2 peaks merge, the actual apparent height of a peak is going to be greater than what it should be, and there's an actual measurement error if you take the height as being the actual height of the peak. And then I'm actually going to go through a derivation of the Purnell general resolution equation, which is really just a different form of the equation that defines resolution. It's an approximation, but it's an approximation written in a way which makes chromatographic sense, and a way which allows you to see what is the problem. Why are the peaks not well enough separated? And there's 3 issues involved. Number 1, is there enough retention? Number 2, are the peaks sufficiently different in their position? And number 3, does the column really have an adequate number of plates to do the separation? If you're working on the wrong variable, for instance, if the number of peaks is already good enough, making it better doesn't generally help you. If there's enough retention, giving the system more retention doesn't really benefit you very much. So you need to know what the nature of the problem is before you solve the problem. And these are the 3 factors I just mentioned. Plate count, or we also call it efficiency, the retention, measured by the retention factor, and the selectivity, or band spacing, all have different effects on the resolution. Then we'll look at a very, very fundamental issue. Is the problem doable? You may be in a situation where it is impossible or exceedingly difficult to do the separation. And you want to know when you're facing that, because you know you could beat your head against the wall and never get an answer. We'll delve into an interesting concept called the effective plate number, which its meaning will become apparent when we get to it. And I don't know that we're going to get to the general evolution problem today, but that's just too far down the list. But these are the main things we're going to talk about today. Okay, so remember the other day I said this is the international definition of resolution. It's 2 times the difference in retention volumes divided by the peak width measured as m, the sum of the peak widths for both peaks, and m is equal to 4 times sigma, where sigma is the standard deviation of the Gaussian peak. As Robert said, this is really the same thing as the difference in retention volumes divided by the average of the 2 peak widths. So algebraically, they're the same thing. Now, this is an important number. If you have a resolution of 1, what it means is that the difference in the 2 retention volumes is about 4 sigma. If the resolution is greater than 1, then the difference in retention of the 2 peaks is greater than 4 sigma. So it's 2 sigma on the side of the early peak and 2 sigma on the back edge of the later peak. It's those 2 and 2 together, the 4 sigma, that gives you a resolution of 1. And a resolution of 1 is pretty good resolution. You'll see this in a minute. But it's not fantastically good resolution. It's not perfect. But it sounds like it ought to be perfect, right? 1. Okay, now these are copied from the Snyder papers. And what he's done here is plotted 7 different pairs of peaks. Both peaks are of the same height, exactly the same height, and both peaks have the same standard deviation. And what he's doing is he's showing you what the peaks would look like if the resolution were only 0.4. You're only going to see one big lump. It's going to look, for all intents and purposes, like a single peak. Now you see this dot here and this dot there? Those 2 dots locate the actual height and position on the horizontal axis of the true peak maxima for peak 1 and for peak 2. Now clearly, there's a big discrepancy between the height of that peak and either of those heights. So you got an analytical error, number 1. Number 2, this peak maximum is not at the same position as the maxima of the well-separated peaks. Now suppose you make the resolution a little better, we get to 0.5. 0.5 is a magic number, and I'll tell you why it's magic in a second. But again, we don't see a minimum between the 2 peaks. It is one peak. But there's a little bit of a plateau where it looks pretty flat. Now if you got a chromatogram that looked like that, you'd say, ooh, that's very suspicious looking. That doesn't look much like a Gaussian peak. And probably I've got 2 peaks that are fused. Again, there's the position of the height and the location of the maxima of the 2 peaks. And there's a discrepancy between the height and the position of the maximum in the fused peaks. You can show with a little bit of calculus that for equal size peaks, for heights that are equal, for equal sigmas, that a single peak is 0.5. If you went to 0.50000000001, there would be an itty-bitty, teeny-tiny minimum between the peaks. There would be two maxima. And now as you increase above 5, and say you go to 0.6, there are two discernible maxima. Now, because the maxima are discernible does not mean that there's no analytical error. Because here's the dot, and there's the dot, and here's the peak maximum, and there's the peak maximum. And so both peaks are a little bit too high, and neither peak maximum is occurring at the right position on the volume or time axis. Both of these maxima are shifted inwardly from the true maximum. Now, let's increase that by just a little tiny bit more, 0.6 and 0.7. No problem seeing two peaks. The dots are virtually bang on. They're virtually, absolutely in the right height and the right position. So if you were to do an analysis by measuring the height of this peak or the height of that peak, it would be pretty darn accurate. And then I'll show you a table in a minute that tells you how accurate it is. Right? Now there's another number on some of these. That number there, which is about 90, and there's the number there, it is 92, and this is 95, and this is 98, and this is 99.4. This is the percent purity. What I mean is, if we dropped a line from the valley, the baseline, and I took all the stuff over here, it would be about, I think that's 86, about 86% pure. And since both peaks are the same height, the other one would be 86% pure, because they're the same, they actually both have the same area. And if I took my valley and went to the baseline and collected the stuff over here, that would be 92% pure. So the deeper the valley, the purer will be the components that you can collect on either side. So 0.5 is one of the magic points. You must have more than that resolution to get two peaks that are the same height to produce a discernible valley. That's number one magic point. The other is resolution of 1. And resolution of 1 is where the two peak maxima are separated by 4 sigma. But clearly, we're not making it all the way to the baseline. So resolution of 1 is not really baseline resolution. Generally speaking, for 1-to-1 peaks, baseline resolution requires, for equal size peaks, it requires a resolution of 1.5. And it will get within well better than 1% of touching the true baseline if the resolution is 1.5. Much better than 1%. Now, 1-to-1 peaks are the easiest peaks to deal with. They require the least resolution to do the job. And one never gets a mixture with 1-to-1 peaks. So this is the best you can hope for. So we go to 2-to-1 peaks. And we can see that life is already a little more complicated. If I come over here to 0.6, clearly the left peak is twice the right peak. There's no valley. There's no 2 minima. That's clearly a shoulder, but it's certainly not, you don't see 2 maxima. Again, the dots mark the position of the true peaks. If they were perfectly well separated, the maxima would coincide with those dots. So, in order to see a clear-cut minimum between the 2 peaks, you need for 2-to-1 peaks, you need a resolution somewhat greater than 0.6. Here's the case of 0.7. In this case, the dot is really in very good agreement with the top of the curve. There's really no error in the earlier peak. But if you've got really good eyes, you can see that this dot is not quite smack on the black. So if you were to measure that peak height, it would be a little bit high, and the peak position would be a little bit off, and so on. Okay, now as the ratio of peak heights gets more and more bigger, gets bigger, you need more and more resolution to get 2 maxima, and you need more resolution to get the baseline between the peaks. So I have a little applet which I'm going to send to you that you can play with. And what this applet does is it lets you change the resolution and lets you change the relative peak heights. So, for instance, a little bit sensitive. Well, that went off scale, didn't it? Well, that's all right. That's all right. I'm not changing the total height. I'm just changing the relative heights when I do this. But you can see. Okay. Oh, this takes it out of the mode where I can write on the screen. Excel doesn't support writing on the screen. And I didn't bring my laser. But there's the second peak. Stands right out, doesn't it? Now, I've given you a very miserable situation to deal with here because the resolution is only 0.6 and the big peak is 16 times the size of the small peak.
8 times.
Yes.
8 or 16?
16.
16 to 2?
No, 16 to 1.
16.2.
Oh, 0.2.
16.
Okay.
Yeah, it's too sensitive. The slider's too sensitive to get it to be exactly 16.0.
Okay.
I guess I could do it this way. If you click the arrow, it comes down in tenths. But let's raise the resolution, okay? Not too bad. Only need a resolution of 0.9. But hey, not too shabby, huh? The point is, it doesn't take a humongous change in the resolution. It's not half bad. So we went from 0.6 resolution to 1.2. We had to figure out, it's easy for me to do this mathematically. It's another problem for you to do it chromatographically in the lab. There's no knob on the instrument that says resolving power increase. That's chemistry. That's why there's job security for people who can do chromatography. But the point is, you only have to double the resolution to take you from a really messy, yes?
With tailing, how do you know the difference between if the analyte is tailing or if it has, or you getting?
Really good question. How do you tell the difference when you have something that just no maxima, it's just like ugly looking on one side? How do you know it's not a tailed peak? And how do you know that it's two peaks together? That's a very difficult question. I'm going to answer it, but I'm not going to answer it right now. There are too many factors involved and stuff you don't know about at this point in time. Okay, I'm sorry
No, that's fine.
to dodge, but I have to. Okay, I'm going to give you this. Play with it. Train your eyeball. Okay? Because you need to know whether or not a separation is good enough. Okay, so I'm going on to the next slide here. And we're going to talk about the cut point and purity. So, what you see here is a split peak, and then under the split peak, I'm actually plotting the two pure peaks that we add together to give the unresolved mixture. Okay, and clearly the maxima are not matching, and clearly the maxima have moved towards one another. This is what always happens, and just think about it. You take two peaks and move them towards one another, the maxima have to move towards one another. They must. They have no choice but to do that. Now we're going to take the cut point at the valley and run it to the baseline. So the PQ line is a fraction. We're going to put in one tube, one beaker, one flask, the stuff to the left and the stuff to the right. We want to ask the question, what's the purity of that cut point? And really what we're asking is, what is the area? Oh, shoot. What is this area? What is this area relative to this area? Well, the other day I gave you those horrific equations with the error function in them, and now we got to use them because we need to know both of these areas, and the ratio of this area to the total area is the fractional impurity of the cut at the valley. With me? It's just a lot of algebra. If the two peaks are the same height and have the same sigma, the valley will be exactly in the middle of the two peak maxima of the retention volumes, or the retention types. So that's where the valley is going to be. It's VRA plus VRB over 2. So we're going to put V in our equation for the area equal to this number. And what comes out of that, the percent impurity of B, which is the second peak, in the A plus B, that's how we would define the percent purity, right? you plug the numbers, the error function equations in, and this is your percentage impurity. Now don't write that down. Because if we use the fundamental definition of resolution, R, the way I told you, the arguments are going to shrivel up to almost nothingness. And by the way, I think it's almost self-evident that for equal sized peaks with equal sigma, if you take the cut at the valley, you lose as much A as B that you gain. I see some heads going, but I don't see enough heads going, right? It's a symmetrical situation. The symmetry demands that this be equal to that. So the denominator, when WA and WB are the same, the denominator is just the total amount of sample that was injected, the total amount of A plus B. And then we got to work on the denominator, excuse me, the numerator. And the numerator, that whole thing turns out to be this, and we replace that with our definition of resolution. Oh, by the way, the ERFC, called ERF, but pronounced error function complement, is 1 minus ERF. So the one-to-one impurity fraction is 0.5 times the error function complement of this. And this turns out to be root 2 times R. So, I mean, the last equation is easy to use. If you think about the total area of two peaks which are overlapping, if you make an error in the measurement of one peak, in the area of one peak, it has to be related to the error that you make in the other peak, because the two peaks have to add up to the same thing no matter where you take the cut point. So that works out to the following result. The percent error in area A times the ratio of the weights or areas, W is the total area, so the weight of A relative to the weight of B. If this is a positive error, then the error in B must be negative. Conservation of area, mass, demands that. And so the percent error in B is the negative of the ratio of the two areas, the true areas, times the percent error in A. Just conservation of mass makes that work out. Some algebra which is gone through in my notes in grim detail comes up with the following formula relating the percent error by height in B peak relative to A peak is equal to the ratio of the true heights of the A peak relative to the B peak squared. So if you make an error here, you have to multiply it by the ratio of the true heights of the two peaks squared, and that will give you the error in the B peak. Now, the real peak is always going to be under the apparent peak. So measuring the peak height can only lead to positive errors. It can never. Again, in my notes, you go through the details of the derivation. The percent error in the A peak works out to be 100 times the ratio of the peak heights. And the bigger the B peak is relative to the A peak, the larger the error is that's going to happen in the A peak. I mean, the bigger the other peak is, the worse off you are analytically. That's almost obvious. And then we have the exponential of all of this stuff. And once again, this all works out to be something directly related to the resolution. And this term here works out to be 8 times r squared. 8r squared. Now, exponential of minus 8r squared is a very strong function of r. And remember, in the example I showed in Excel, we doubled the resolution. We went from 0.8 to 1.6, I think. We doubled it, and voila, that second peak, even though it was 16 times smaller, you could see it easily. That's a consequence of this exponential 8r squared dependence. If you put in r twice as big as the previous r, you have exponential of a negative 4 times bigger exponential. That's a big change in the argument for the exponential, so the error goes way down. What this means is the following, and it's very important analytically. Getting two peaks to decouple is much easier if you evaluate it in terms of the height of the peaks rather than the area under the peaks. It's easier to separate them by height measurement than by area measurement. And here's a plot of that. This is the error in height of one-to-one peaks and the impurity fraction of one-to-one peaks as the resolution gets bigger and bigger. And you see that out here, when we have somewhat decent resolution, a resolution of 0.4 is completely indecent resolution, because with one-to-one peaks, you can't see two peaks. You're only going to have one maximum. So out here, where we have, say, 0.6 or better, the error in the peak height is way smaller than the error in the fractional impurity, and therefore any area measurement, it would be much more difficult than a height measurement. And now when we get out here to say 1 or 1.2, there's virtually no error in the peak height. Here's some numbers. This is for one-to-one peaks. Okay. There's a resolution of 1. The error in the peak height in percentage for one-to-one peaks is 0.03. That's so small that you couldn't reproducibly measure it. Right? So it's an insignificant error. On the other hand, at this resolution of 1, there's still about 1.6% contamination of one side of the peak with the other side of the peak. And to get even to an impurity fraction of 0.35%, you've got to get out to a resolution of 1.8. Now, doing the calculation for different size peaks, different peak ratios, obviously as the ratio becomes more and more greater, the big peak is easier to measure, but the small peak becomes harder and harder and harder to measure, and you need more and more and more resolution to measure the small peak to a given percent accuracy. But with a reasonable degree of resolution, it's always easier to measure things by peak height than by peak area. we'll have a lot more to say about whether one should measure peak or area when we talk specifically about different kinds of detectors, because there's some other issues, very important issues, that come into play as to whether you quantify the peak by measuring its area or quantify the peak by measuring its height. Someone once asked me, is it better to integrate the peak by area or by height? And you can't integrate by height. It's a nonsense word. You can quantify by height and you can quantify by area. The area requires integration. Okay, back to our friend, the definition of resolution. I'm gonna mess around with it a bit, and I'm going to assume that both peaks have the same end value. They have the same plate count. They have the same theoretical efficiency. And I'm going to plug this in here and then put the force VR over root N in there, and then boom, I get this equation. The width is now really built into that parameter, the number of plates. Okay, that's just 2 steps in substitute. Now I'm going to do something a little sneaky and introduce a new concept. I'm going to introduce the concept of selectivity. And we define selectivity that by always putting the more retained peak over the less retained peak. And it's defined as the ratio of the retention factor of the more retained peak over the retention factor of the less retained peak. Therefore, alpha must be greater than or equal to 1. If the 2 peaks absolutely coincided with one another, alpha would be 1. Now I'm going to take this definition and the fact that my retention volume is equal to the dead volume of the column plus the retention factor of the column. Remember, I told you that this was like the most important result of the plate model, so I'm going to use it now and substitute this in for all of the retention volumes. And I think it's evident that the VM, the dead volume, has got to cancel out. And I wind up with this equation. Here's the resolution, there's N, here's the selectivity, and then there's a bunch of terms involving the retention factors. I can mess around with this a bit more. And put it in this form. And when I put it in this form, I'm going to make the approximation that the 2 peaks are pretty close together. This is very important. Listen. In order to get this equation, I'm going to assume that K prime A plus K prime B over 2, that the Ka and the Kb are about the same, because I only care about resolution when the 2 peaks are pretty close together. If the 2 peaks are miles apart, you know, it's well resolved and you don't care. It's only when they're close together and alpha is only a little bit bigger than 1 that you care. But if that's the situation, this approximation, and it's an approximation of the... So we see that resolution depends upon 3 factors. It depends upon the efficiency or plate number. It depends upon the selectivity, also called band spacing, and it depends upon the amount of retention. Now, some people write the equation like I have on the left. Other people say, look, in order to derive this dumb equation, you've had to assume that alpha is close to 1. So if alpha is close to 1 already, write it as 1. So you'll see this written either way. I like this form a little better. It turns out to be not quite so much of an approximation as this second form. So, as I said in the outline, if a separation is bad, it can be bad for 3 different reasons. You may not have a high enough efficiency on the column. You may not have a high enough selectivity of the mobile and stationary phase and the temperature working together. Or you just might not have enough retention. I'm going to run it backwards. The first law of chromatography is if you don't have retention, you can't get resolution. If K prime here is 0, it doesn't matter if you have a gazillion plates. And it doesn't matter if the alpha is really big. You're not going to get a separation if the first peak is totally, completely unretained. You have to have retention. Okay? Now I can take this equation and flip it around. And I can say I'm going to put n on one side and I'm going to put everything else on the other side of the equation. And I can calculate how many plates I need to do a separation if such and such is true. So I'm going to consider 3 cases. K prime equal to a half, K prime equal to 1, K prime equal to 5. And I'm going to look at a number of different values of alpha, the selectivity. Now, if K prime is a half and alpha is 1.01, this says that you need 1.5 million plates to do the job, to get to a resolution of 1. Now, 1 is not a perfect separation. If the K prime is somewhat bigger, if it's 1, gee, the number of plates needed drops by almost a factor of 2, down to a mere 650,000 plates. And if you jack the K prime all the way up to 5, the number of plates drops to 230,000. I don't care what the retention is, 230,000 plates is a lot of plates. It could take you a very long time. The column would have to be miles long to get that number of plates. This is a real bad situation to be in. If you were doing very high resolution capillary gas chromatography, yes, you could generate 200,000, 300,000 plates. It would probably take you a couple of hours on a very long column under absolutely optimized conditions to do that. If you had 100 samples to run, you'd be up the creek without a paddle. You'd be in trouble. But 100,000 plates in capillary GC is not out of the question. If you're using a packed bed GC, 10,000 plates is more like it. If you do an HPLC, 50,000 plates is possible. It's going to take a while. If you were doing electrokinetic micellar chromatography, 100,000 plates is a possibility. It would take a long, it would be a long run. But the really interesting thing is look at what happens to the required plate count when alpha changes, not a lot. Let's come down here to alpha of 1.1. That's 17,000, that's 8,000, that's 2,800 plates. If I get a 10 centimeter HPLC column and I can't get 20,000 plates on that, I'm going to send it back to the manufacturer. This is, for LC or GC, a very easy, very doable separation. Up here in LC land, 150,000 plates, I'm sorry, 1.5 million plates, forget about it. It's been done. It's been done. Somebody did some capillary gradient dilution LC. I believe the run took 48 hours, and they got 1.5 million plates. It was a joke. You know, it was. They needed some numbers to get a proposal funded or something like that. I don't know. But it's not a practical separation. Just not a practical separation. So if you're up here, what are you going to do? Make your column longer and longer until you get enough plates? I don't think so. You're going to change the conditions. You're going to change the column. You're going to change the mobile phase. You're going to change the temperature. You're going to change the pH. You're going to do something to get alpha not to be 1.01, to get it more like 1.1. So the answer to that, you know, is at a certain point, you have no hope of generating enough plates. So you've got to work on a different variable. Here's what a plot of the resolution versus retention factor looks like. Doesn't matter what n is, it doesn't matter what alpha is, the plot looks like this. It goes up rapidly, starting at no retention. It goes up very rapidly, and it rolls over and flattens out. And if the retention, this is 5 here. But if a retention factor was bigger than, was say 10, it would be within 1% of the horizontal asymptote. There's never a reason to make the retention factor of a compound bigger than 10 in terms of resolution. It doesn't help. But it makes a lot of difference if your resolution, if your retention is close to the dead time or dead marker or dead volume of the column and there's no retention, and increasing it somewhat. It makes a big difference. It just goes shooting up. So again, I remind you of the first law. If you don't have retention, you're not going to have resolving power. You can't. No matter what else is good, you're dead. Here's a couple of plots of resolution versus efficiency. This has no asymptote. It just keeps going up and up and up and up and up. It's curved because it's a square root relationship. By the way, this is not 0 over here. It's 100 units of efficiency, and it just goes up as a square root. And A, B, and C are just different values of K prime, 10, 3, and 1. And in all cases, alpha is assumed to be 1.1. But the shape of the curve really doesn't depend on this or that. It's a square root relationship. Which is unfortunate, because if you need to double the resolution, what do you have to do to the number of plates? You got to square it. You need 4 times the number of plates. That's not a favorable situation. Selectivity. This starts with a selectivity of 1, which is the lowest possible ratio of the 2 peaks, and then goes up. but it goes up very, very, very rapidly as a function of selectivity. And note how close these get together as K prime gets bigger and bigger and bigger. After 10, there's just not much more to be gained by going to 20 or 50 or 100. You're just not going to help yourself. And of course, you're putting a gun to your head in terms of time, because if your K prime goes from 20 to 40, your analysis time just doubled, and you got nothing for it. Time is very expensive. This is the last plot. This is the last. I want to end right here. I can combine all of these concepts in this one slide. The first time I saw this, it was in Yun Mao's one of her papers. She was very interested in the effect of selectivity on separations. We got 3 different axes here. But just look at this curve, and you'll see that alpha really has a major impact on the resolving power. Alpha is probably the most important property for getting a separation to work. Okay, let's knock off here. Almost up. There may well be a quiz on Monday. We've covered another chunk of material.